Hello, good afternoon, everybody in this part of the world, in Europe, Poland. To you, I say good afternoon. For people who might be on the other side of Atlantic, good morning. It's a great pleasure to welcome you for our, I believe, 14th virtual seminar in computational science. My name is Marek Michalewicz. I'm the director of ICM. And let me very briefly acknowledge our partners and supporters. We have honorary patron, which is National Information Processing Institute in Poland. We have media partners that Datanami, ITWiz, HPC Wire, Computer World, Enterprise AI. As you might know, some of you have followed our series of lectures. We've been running them since around April, perhaps June last year. We had 13 of them. And here's the list of all the previous speakers. We're very, very fortunate to be able to invite the most outstanding sort of trendsetters, thinkers, and influencers in our fields. You're, of course, most welcome to look at our website. All of our lectures are recorded, and you may wish to sort of browse through, and if something catches your interest, please follow the lecture. I wish to announce that ICM will be organizing the 7th Supercomputing Frontiers Europe conference. It will take place virtually this year, as it did last year. Last year it was in March. This year we decided to move it in late July, early August time frame. We haven't set the date yet. At the moment we have very, very strong support of scientific committee. Will be calling for contributions very, very soon. So watch out this space. That might again prove to be very, very interesting for many. Something very important for ICM, for us, there is a special competition to open scientific center of excellence. It's called Discovery. There are going to be 10 such centers in Poland. Financial conditions are really excellent, not even for Polish conditions, but also European and world. So welcome all interested people who might wish to consider relocating to Warsaw, working at ICM. ICM will provide partial funding for that. And if you are sort of thinking of starting your own research group or continuing from wherever you are, I'll be very happy to talk to you. It's open. And now let me introduce our speaker of today's talk. It's Professor David Bader, who is the director of the Institute for Data Science at New Jersey Institute of Technology. Prior to this appointment, Professor Bader served as founding professor and chair at the School of Computational Science and Engineering, College of Computing at Georgia Institute of Technology. He is a fellow of IEEE, AAAS, and CIAM, and advises the White House, most recently on the National Strategic Computing Initiative. Dr. Bader is a leading expert in solving global grand challenges in science, engineering, computing, and data science. His interests are in the intersection of high-performance computing and real-world applications, including cybersecurity, massive scale analytics, and computational genomics. And he has co-authored over 250 articles in peer-reviewed journals and conferences. Dr. Bader has served as a lead scientist at several DARPA programs, including high productivity computing systems with IBM, ubiquitous high-performance computing with NVIDIA, anomaly detection at multiple scales, power efficiency revolution for embedded computing technologies, hierarchical identify, verify, exploit, and software-defined hardware. He has also served as director of the Sony Toshiba IBM Center of Competence for the Cell Broadband Engine Processor. Bader is co-founder of the Graph 500 list for benchmarking big data computing platforms. He is recognized as a rock star of high-performance computing by Inside HPC and as HPC Wire's People to Watch in 2012 and 14. In April 2019, Bader was awarded an NVIDIA AI Lab Award, and in July 2019, Professor Bader received a Facebook Research AI Hardware Software Co-Design Award. So with this very impressive, I know Professor Bader for many, many years. We sort of see each other at every sort of big conference like Supercomputing or ISC. So it's a great, great pleasure for me to finally welcome him virtually in Warsaw. Welcome, David.
Thank you very much. Thank you very much, Mark. It's a kind introduction, and I look forward to our paths crossing again in Warsaw or at Supercomputing, and the days when the world is back to normal again. So as you've mentioned, my talk today is on solving global grand challenges with high-performance data analytics. I've recently moved to the New Jersey Institute of Technology, so let me just tell you in a few slides about NJIT. We recently jumped into the top 100 in the United States for college rankings, so it's an upward trajectory for a research school that is in the New York, New Jersey metropolitan area. The New York Times has ranked us #1 in upward mobility for any school in the country in the United States, and that is colleges that are ranked by the percent of students from the bottom fifth of the income scale who've moved up to the top 3/5. So it's a very scrappy type of school where we have a lot of first-generation students. About a third of our student body is the first member of their family going to college. And we put many, many students out into the job market. In fact, we're the top producer of computing talent among schools in our region, and that includes Rutgers, which is our neighbor, NYU, and other programs. As mentioned, I'm a distinguished professor and direct a brand new Institute for Data Science, which has about 35 participating faculty. We have 3 existing centers: the Center for Big Data, which covers big data analytics systems and tools, and a lot of the research in cyber infrastructure. We have a cybersecurity research center focused on practical encryption and privacy technologies, a medical informatics center focused on biomedical ontologies, working closely with NIH and the National Cancer Institute. And we're in the process of launching 2 new centers, one in financial data science that would serve the financial services and insurance industry, and also a center focused on machine learning and AI that we should launch this year. I also hold a weekly seminar series, Wednesdays at 4 p.m. Eastern Time. The lectures are also recorded on YouTube where they're live streamed. And so if you search for NJIT Institute for Data Science on YouTube, you'll find some of the great speakers that we've had there. So here's a picture of Jersey City from looking at it on the Manhattan side. We're just one pass stop away from Lower Manhattan. So we have a number of students who are working in the fintech sector or working within Northern New Jersey who are attending our classes focused on data science and computer science. Here's a great aerial view looking at Jersey City from one of the towers in Manhattan. And you'll see the Hudson River in the foreground. And if you scan over to the right past Goldman Sachs, 99 Hudson, you'll see another tower, which is the Bank of America building. And what's highlighted in red is where my office sits on the 36th floor. And this is our Jersey City location. So if you're ever in the area in the US, you want to visit, come. You're welcome to visit us here and see what's taking place. So my institute focuses on solving real-world challenges, and that includes problems from urban sustainability, healthcare analytics, trustworthy, free and fair elections, insider threat detection, giving attribution to cyber attacks, and other sorts of work where we use real-world data and we apply high-performance computing algorithms and infrastructure in order to find meaningful solutions to problems that affect our global population. I've been really pushing the envelope on data science. For instance, under the Obama White House in the US, I was a part of the planning for the National Strategic Computing Initiative that was launched by executive order in July 2015 to really advance the US leadership in high-performance computing. The area of data science has been growing and really blossoming. We've seen its uses across healthcare analytics and in basic science and engineering computational fields that have become, have really moved forward what they're able to do given data and making data-driven decisions. That National Strategic Computing Initiative was updated under the previous White House administration, and on the 14th of November 2019, the update to NSCI was released. I was a part of this activity for pioneering the future of computing that put in place a 10-year plan on the types of developments that we'll need with software infrastructure, with overall hardware and cyber infrastructure, as well as partnerships across academia, industry, and government to continue our pace of innovation related to data and computer science at the high end. Here you'll see my 15 minutes of fame on Twitter, where I announced this new report, and the US Chief Technology Officer at the time, Michael Kratsios, retweeted my announcement. So as mentioned in the introduction, I've been working very closely with NVIDIA on a number of projects. I direct an AI lab with NVIDIA, or an NVAL award, where we're building open source analytics in a toolkit called Rapids AI. And the work that I'm going to talk about today has derivatives that have been integrated into NVIDIA's solution for accelerating open source data science. I've also been working with Facebook and their AI systems on a representation learning problem called scalable graph learning, where we're moving from a problem that could be solved, say, on a desktop, to understanding how to solve enterprise scale problems in graph representation learning. So we're taking algorithms and applying high performance computing for this very important machine learning problem. Now, what I want to talk to you about today, let me explain this chart to you, this quad chart. And here in this presentation, you see the whole chart. Normally, I would walk through it step by step. So let me start with the two axes, where you see objects on the x-axis. So I have known objects on the left side and unknown objects on the right side. And then the y-axis is patterns, where I have known patterns at the bottom and unknown patterns at the top. So if we look through these four quadrants that I have, let me start on the lower left, where I have known objects and known patterns. This is an area where traditional relational databases from the 1980s have performed extremely well on being able to understand data science problems. And for instance, we may have customers in a store purchasing particular items. I want to understand the people and the purchases that are made. And since the 1980s, we've been able to solve these types of problems very well. If I move to the upper left-hand quadrant, where I have known objects but unknown patterns, here, let me give you an example from cybersecurity. I may have an individual in my company, so I know everyone that person is interacting with, but I may have an unusual flag or an event raised. I want to inspect, what is that employee doing? Are they colluding with others? Are they trying to exfiltrate data and IP? And so this is a place where where vertical databases, for instance, designed in the 1990s, have been very effective. So where I've known objects, but I'm trying to explore around them and the patterns that they're generating. If I go to the lower right quadrant, Here I have an example of a known pattern or motif and unknown objects, for instance, observed activity. And what I'm trying to do is pattern matching or subgraph isomorphism, where I take a known motif or pattern and find it within those data sets. And that's also been a problem that we've been able to solve heuristically fairly well for several decades. But where I want to focus is this upper right-hand quadrant, sometimes called the fourth quadrant or unknown unknowns, where I have new data and I'm trying to do a problem of discovery, of understanding what power that data has. I want to minimize surprises, and I want to move data out of this unknown unknowns and move it to I start have understanding of what's happening within these data spaces. So this is the great unknown, and the techniques that I'm going to talk about today are very useful for exploring this quadrant of data science. I tend to think of these problems in terms of graphs, where graphs have vertices and edges which represent the relationships between those objects. We can use this abstraction in many real-world challenges, for instance, in healthcare, for understanding the detection and spread of pandemics. For instance, we have the COVID SARS virus that's now spreading. In massive social networks, trying to understand communities and their intentions, even how pandemics spread, transportation systems, evacuation due to severe events. For business intelligence, within systems biology for understanding life itself, the electric power grid that's responsible and important for communication systems, transportation, energy, water, food supply, even performing full-scale economic, social, political simulations of entire nations. All of these involve graph data science, and I claim that they use exascale, meaning very large data sets, and the notion of streaming graphs or graphs that change dynamically over time when faced with a fire hose of new observations. So these types of problems really require us to predict and influence change in real time and at scale. There are many different types of graphs. Graphs are really pervasive in these large-scale data analyses, but the sources of the data that we have may come from large-scale simulations, that may come from experimental devices, the internet, scientific applications, or other types of sensors. So let me just give you an example or three examples here. On the left-hand side, I may have a graph problem coming from astrophysics, where I have images from digital sky surveys. And what I may want to do is find pulsars and move a telescope to look at these pulsars in the fleeting minutes that I have to observe a pulsar in action. So I may take different images of the sky and overlay them looking for outliers, an object that exists in one image but not in the other. So to perform outlier detection, I have these massive data sets. There may be temporal variations in the data, and the graph type of problem I want to run is either clustering or matching between objects. In the middle, I have an example of a problem from bioinformatics where I want to identify drug targets. And the challenge is that I have data heterogeneity as my observations are collected from multiple laboratories. There may be very different quality among these data sets. And the graph problem that I'm trying to solve may be in an algorithm like centrality or clustering. While on the right-hand side, I have an example from social informatics or social networks, where maybe my problem is to discover emergent communities or model the spread of information or disinformation. And the graph problems that I may want to solve look like clustering problems or shortest paths through the graph or flows of information through the path. And here I'm challenged by potentially needing new algorithms, new analytic routines, uncertainty in the data, missing data. So in all of these three cases, they're graph problems, but my challenges come in the face of having very different data sizes, heterogeneity in the data sets, uncertainty in the observations, and also the quality of data. So these are some of the challenges that we face. So for example, I mentioned the electric power grid. In the United States, we basically have an east and west power grid in the country, and there's about over 150,000 miles of line. And we try to use graph analytics to discover and make more resilient parts of this network. In fact, in the past, we've worked with the Pacific Northwest National Laboratory in the United States to try to shore up the US power grid. There's also good examples of graph analytics coming from intelligence and surveillance. The top example that I have is a public graph of the hijackers on September 11th in the US. And it was argued that if we could have run graph analytics and an analytic routine called betweenist centrality, we would have been able to pick out the hijackers from this data and even the ringleaders of the operation. On the bottom is another type of problem where we may have a pattern. For instance, here are two people that live together and are observing a building. One rents a truck and one purchases fertilizer. Maybe they're constructing a bomb. And what we may want to do is observe background data to see if we find that pattern within observed activity. So this is an example of detecting anomalous activity by using either exact or approximate graph matching, or the subgraph isomorphism problem, where we're looking for this motif, and we may find it exactly in the data set, or we may find it with dilated edges or missing edges or objects, but we may find things that are close to that pattern. So these have proved to be very important techniques. And through my talk, while I may use the notion of social networks, we were the first group to apply social network analysis and parallelize betweenist centrality algorithms for looking at the human proteome. And this is just a snippet of the results that we had, where every one of these dots on this log-log chart represents a protein. On the x-axis is the number of other proteins that it interacts with on a log scale. So on the right-hand side, we have proteins that are highly reactive within the observed interactions. And on the left-hand side are ones that don't interact much at all. And then on the y-axis is a normalized betweenist centrality score. So how important is that protein within the human proteome? So the top is high betweenist scores, and the bottom is very low betweenist scores. So what we found is the protein with the highest betweenist centrality score in the human proteome of about 44,000 interactions available at the time. That protein was implicated in a breast cancer. And it was like a needle in a haystack. It wasn't the protein that was most reactive or interactive within a cell, but it was one that was kind of hidden, but very important for the operations in that cell. So these are the types of algorithms that we're interested in. And we often go through a flowchart when we decide how to solve these types of graph-theoretic computations. For instance, we take our input and we figure out how to abstract it as a graph. What are going to be vertices and what are going to be edges? And then the type of graph analytic problem that we're trying to solve for. For instance, are we finding paths? Are we looking for clusters? Are we trying to partition the data, do matchings, locate patterns, order, and so on? So we figure out the graph problem. And once we know the graph problem, then it informs us as to what graph algorithms are available to solve that problem. Is it a traversal problem? Do we need shortest paths, flow algorithms, and so on? But some of those decisions then have to be influenced by the qualities and characteristics of the graph that we have. For instance, is it a dense graph or a very sparse graph? And by sparse, I mean the ratio of edges to vertices within the graph. Is the graph static or does it change over time? Are there weights on the vertices, weights on the edges? If there are weights, do they have a particular distribution? Are the vertex degrees held in some distribution? I should define the degree of a vertex as the number of other vertices that it's connected to. So is it a constant number, like a road network where the average degree may be 4, or is it something like a social network where I have many, many vertices of low degree and then a few very high degree vertices? So I take all of these factors and I put it together to then figure out what is the graph algorithm, and then I look for platforms where I could solve it. I may often recast the problem as a sparse linear algebra problem. For instance, in partitioning, we do this with spectral methods, or maybe I can use linear programming, for instance, in matching problems, or do I use an ad hoc graph solution directly to solve the problem at hand? Today, we have many high-performance computers that are great for graph and data analytics. So for instance, traditional high-performance computers I characterize on the left-hand portion of the slide that are really wonderful for static data sets where I can load in the data set and analyze it. And I have massive scalability, but I have to do very regular operations. So this makes these systems great for dense problems, and sparse problems typically underutilize this system. Today, we're moving towards streaming analytics on the right that really requires specialized analytics and data structures to be able to capture the fact that the data is changing rapidly. And I also have low data reuse, so I become focused more on memory operations rather than floating point operations. So as we move from traditional high-performance computing to new streaming analytics, it moves us from reporting the news in traditional HPC to being able to do predictive analytics and strategic foresight in streaming analytics, where we are able to predict the future and then change before there is some egregious event. Oftentimes today, when we think about large-scale data science, what we're doing is taking a data set after there's been a failure or after there's been a breach into an organization. For instance, if a company is intruded upon, we take all of the system logs, we analyze them, we try to find out where the intrusion occurred, what the intruder touched, what they saw, and what they took or exfiltrated. So we're often looking at problems after the fact and reporting on the inverse problem of how it occurred. Versus in streaming analytics, we're really trying to get out in front of the problem and solve scenarios before they become problems. So again, I think this is a very key aspect of what we're able to do with graphs and discovery. So as we move to graph data science, we need to research, are there new graph techniques? Do they scale to the size problems that we have? Can the computational systems that we have handle these massive networks with billions, trillions, or more of items? And can they tolerate the noisy data, the massive data sets, the streaming data sets? Let me move forward here and just give you an example. Again, I'm going to step through this chart with you. What happens is on the left, we have some real world actions that generally create tuples or relationships. For instance, we have objects here, A and B are in the first object. There's a timestamp here, T1, and some action like a poke. So maybe at time 2, there's 2 tuples. The first one is A is sending a message to C at time 2, and maybe at time 2, B is receiving the poke from person A. So whatever our application is, we may abstract it by these tuples, and each one of these tuples will create an edge with attributes. So we're going to funnel all of these edges into a computer, a graph analytic computer, that is going to form a state of the graph where the vertices may have types, the edges may have types, and this may grow rather large. We have a writer process creating it, and then we have these analysts who want to ask questions of the data and explore in a data-driven way, and they may ask multiple questions concurrently of this growing graph data set. So this is the operation that we've been working with in streaming graph data science. And once you think about this regime, you start to think about interesting analytics that you could ask. The The categories that I divide the analytics in are primarily three categories. The first category is a straightforward extension of inserting time into traditional graph analytics. So for instance, you may have a windowing operation, such as the question, are there paths between vertices S and T in the window of time between T1 and T2? Or you may have a snapshot question, what were the important vertices at time T? So these classes of analytics are the ones that you normally think about once you add time to graph data science and you're trying to solve streaming problems. But there's two other categories that are much newer and emerging as areas that need more research to determine the types of queries and algorithms that we can employ to solve these problems. One is change detection. So can we deploy persistent queries to monitor properties? For instance, does the path between vertices S and T shorten drastically? And if it does, alert me when that happens. Or is there some vertex that was kind of hidden previously, but suddenly became very central in the graph? Alert me to that change. So the second category is really change detection of static properties. The third category is what I call fully dynamic graph queries, where I want to look at an analytic that only has a temporal sense to it. There's no static analog. For instance, does a small community stay independent over a long period of time rather than merge with a larger group? Or when does a vertex that was core in one community jump to a different community and become core in a different community? So these are some of the most interesting analytics where I'm taking full use of that dynamic or temporal nature to try to understand changes structurally within that graph. So as an example, we were the first group to do an analysis, a complex graph analysis with every public tweet. So we took all of the public tweets jointly with Pacific Northwest National Lab, and we streamed them into a supercomputer at the time that was very good at doing graph analytics, here the Cray XMT. And we created a graph with the followers and followees on Twitter and tried to run an analytic like between a centrality to tell us who are the most influential Twitter handles during breaking events. So we looked at a couple of events. This was in September, October 2009. And we took a breaking event such as the spread of a pandemic of the day, H1N1, a variant of the influenza virus. And we were able to get out the top 15 handles in terms of influence and where people were getting their information. And this was this supported our notion that we could use these tweets to try to tune into the most important information sources. So at the top ranked position, number 1, is the US Centers for Disease Control and Prevention flu line. We also see number 4, flu.gov. Numbers 12 and 13 are also the CDC. Those are all coming from the official government notification systems on the flu. There's also commercial media. For instance, number 5, the New York Times. Number 8, CNN. Number 11, Time Magazine. And this also confirmed our conjecture that we would find news sources, traditional news sources, that were very influential. But our surprise and shock came with, say, number 3, this handle, official PAX. We had never heard of this handle before, and it turns out it's probably not the group that you would tune to in a breaking event to understand the mortality rate and symptoms of a new and novel virus. This was the handle of a group of mostly adolescent males at a gamers conference called Penny Arcade. And they were meeting in September of that year in Seattle, Washington. And it turned out that this group was the first group in the United States to all contract H1N1. And they started tweeting with each other the symptoms, whether or not they were alive or dead. And it turned out that this virus fizzled out. It was predicted to have double-digit mortality rates, and it turned out to not be as deadly as presumed, which was a good event. But during these breaking events, you would never have known or thought to tune into this handle. So graph analytics gives us that capability during breaking events to take a lot of information and disparate types of data, pull it together quickly, and try to make sense and understand what's there. We have launched an effort called STING, Spatio-Temporal Interaction Networks and Graphs, which is really the software support needed for solving these types of real-world graph problems. And there's a number of challenges that we face, including the sparsity of the data sets and the lack of locality for these problems in the massive data sets. We have to co-design architectures along with algorithms to handle these new streaming problems. And we need new supercomputing designs that are energy efficient, resilient, and easy to program for these types of graph data science problems. This is an area where we've been developing in for now over a decade, where we initially released a design of a data structure called Stinger in 2009, and had a number of firsts since then for dynamic graph algorithms, including the first clustering coefficients algorithm, tracking of streaming social networks, maintaining betweenist centrality over a dynamic graph. We've won some best paper awards along the way, tracking connected components over time, having the first incremental PageRank algorithm that updates PageRank based on the updates to the graph rather than recomputing from scratch each time. And then a number of years ago, we accelerated our work using GPUs in a framework called cuStinger and then renamed as Hornet, which is now integrated in some of NVIDIA's Rapids AI open graph accelerated solutions. And here we've looked at triangle counting, keeping track of K-trusses within a graph, dynamic cat centrality, and other algorithms that have been accelerated using GPUs, even including multiple GPU algorithms, for instance, having the first multi-GPU breadth-first search on a massive graph. So Sting is really a data structure that lets us implement these dynamic graph algorithms where we imagine that we have a single writer to update the graph and then potentially many readers at the very same time accessing that graph, which sits in a globally addressable shared memory, either logically or physically, where we can store that graph and update it, where we often don't have time to copy the graph or optimize the graph data structure itself. We're just trying to keep up with the ingestion rates from the stream at the same time as running analytics. This is kind of an eye chart of what the data structure looks like, but we essentially have a extensible vertex array and then blocks of edges. And because this is a block data structure, we're able to use parallelism across the vertices and across the edges. And we also have indices of different edge types so that we can look at a graph and maybe we have edges that are red, edges that are blue, edges that are green. And we may run an analytic that says, I want to operate a graph analytic, for instance, connected components on the red and blue edges, but ignore the green edges. So we're able to filter the graph by looking at just particular types of edges that we have. So this package has been in development for a number of years, and all of this software is open and freely accessible. Today it sits on GitHub, where you can access all of this code. So why not existing technologies? It turns out that traditional SQL databases really don't have the ability to handle this structured information for meaningful graph queries with any sort of efficiency or timeliness. There's a lot of work on graph databases where the graph is mostly stored on disk or Hadoop and HDFS-based projects where all of the data sets are stored on disk. And when you're running graph analytics with this lack of locality and you are jumping between edges in the graph, you really need the graph to reside in memory, even if the memory is distributed, rather than working at disk speeds that could slow you down by 5 or 6 orders of magnitude. There's a number of graph libraries out there that have been very successful, but often they're limited to the size data set that you could fit on a laptop, and they don't scale beyond, say, 1 million vertices or beyond the memory constraints of a few gigabytes. We're often looking at graphs on tens of terabytes and trying to run graph analytics at scale. So just to give you a couple examples, I have 3 case studies of different graph analytics, just to give you a feel for what it means to do dynamic graph problems. Here is the notion of clustering coefficients in a streaming graph, and clustering coefficients are really counting the ratio of actual triangles to possible triangles around a vertex. So if you look at the literature, you'll see a lot of efforts trying to do triangle counting, and it's really to discover the clustering coefficients. They're a very good surrogate for community detection. So here we have a vertex I connected to vertex J and vertex V. So this is a closed triangle IJV. We also have an edge from M to V and N to V, but maybe we're missing the edge between M and N. So this is what we call an open triplet, not a closed triplet. So what we want to do around V is find the number of closed triplets or triangles rather than just open Vs. What we've shown is that if you add an edge to the graph, you can just update the cluster and coefficient counts in a local neighborhood around those vertices that are adjacent to that edge. So we have a fast method that is both either exact or approximate, where we can keep tracking clustering coefficients as edges are both added and also deleted from the graph. This gave us a study where we tried to look for the optimal batch sizes, and what we discovered is in streaming graph analytics, you never want to do single updates. So B equals 1 gives us a rate for single updates. That is typically poor in any solution, but as long as you have thousands of edges at a time that you want to batch update within a graph analytic, that seems to be the sweet spot of what we've found through the years and systems. So 1,000 edges or a couple thousand edges is normally a good batch size. Here's another example analytics of tracking connected components. So this has more structure involved, and on a connected component, if we're inserting an edge into a graph, it's a pretty easy operation. We look at the 2 endpoints of the edge, and if they're already in the same component, nothing's changed. But if they're in 2 different components, we then merge those components together. So inserts are pretty straightforward, but a delete becomes much harder. When we delete an edge from a graph, we have to decide, is that edge, which is being deleted, cleaving off a component or breaking a component into multiple pieces. So we have to prove that it's a safe delete and doesn't do anything, or that it's a delete that's going to cause new components. So it turns out that we've been able to solve this, and I'll just give you a little snippet, that the results were that we could very quickly prove that deletes were safe and do that very fast. So 99.7% of the deletions in a social network graph typically are safe deletes that we can prove very quickly won't cleave off a component. So for instance, if the edge is not in the spanning tree, if the edge endpoints have a common neighbor, or if a neighbor can still reach a root of this spanning tree, then we say that that deletion doesn't cleave off a component in the graph. And every so often, we may have to run connected components from scratch for a very small percentage of deletions that may cleave off a component that we weren't able to prove are safe in a fast way. My third case study is tracking betweenist centrality in a streaming graph. This is a very important analytic that computes the number of shortest paths that go through a particular vertex divided by the total number of shortest paths in the graph. So this is computationally expensive to do in an exact manner. And we've been able to keep up with betweenist centrality in a streaming graph by tracking the edge insertions. And we've had speedups 1 to 2 orders of magnitude from looking at our new streaming betweenist centrality algorithm when compared to statically recomputing the betweenist centrality as the graph is updated. So just to conclude this talk, solving these massive scale analytics really requires new hardware-software co-design, new high-performance computing platforms, and understanding the impact that streaming algorithms, streaming data science is going to have on the architectures. I didn't mention it much through this talk, but energy efficiency is also a principal design component. We're going to need to design chips, systems, and data centers that really can process these graph data science data sets and do it in an energy efficient way. Now, doing this may create solutions that are 6 or more orders of magnitude faster if we choose the right architectures for the right problems that we have. And this is something that we can't afford not to do. It's needed for real world challenges, some of which that I mentioned during this talk in urban sustainability, healthcare analytics, trustworthy free and fair elections, insider threat detection, the utility infrastructure problem, cyber attack defense, and disease outbreak and epidemic modeling, just to name a few. I also want to thank a number of researchers and former students that have contributed to the work in this talk. Oded Green, who was a PhD student with me and also a research scientist. He's now working with NVIDIA. And then some of my alumni, Dr. Isha Nathan, she's now at Lawrence Livermore National Lab, Vipin Sachdeva, Anita Zaskrushka, who is with Trovaris, Dr. Luis Miguel Munchula, who's at Google, Kamesh Maduri at Penn State, David Ediger at GTRI, James Fairbanks, who's now a professor at University of Florida, and Dr. Sunghwa Kang, also at NVIDIA. So it's really a lot of my students' hard work that has been presented in a number of the results that I have here today. So I want to thank you for your attention, and I would love to take any of your questions. So I see in the chat there's a question. How vectorizable and or parallelizable are the algorithms being used now? Sting, presumably quite parallel given that you used a XMT and in the future. So let me answer that first. While Sting was initially designed on the XMT, it really used pragmas within the XMT for identifying where there was parallelism. The XMT was a machine ahead of its time. So this was a machine available about a decade ago. And we took those pragmas and we ported the infrastructure that we had to systems with OpenMP. So if you have a processor system, for instance, x86 class with many cores and a large memory, you can run Stinger on it using OpenMP. We've even ported Stinger down to a very small scale and ran it on a Raspberry Pi. And whether or not you have 256K of memory in the Raspberry Pi or some several terabytes in an Intel multi-core system, the amount of memory you have really dictates the size of the graph you're able to keep persistently. And that size is going to tell you whether or not you're able to manage a couple minutes of data, for instance, on a Raspberry Pi, or maybe decades of data on a modern HPC system. And so Stinger is still in use and the code is still in development. It's also been derived, for instance, Hornet on the NVIDIA GPUs is a derivation of Stinger that runs on commodity GPUs. So question 2, is there an application that would be amenable to quantum computers? Oh, sorry, is this an application that would be amenable to quantum computers? So the answer to that is absolutely yes. We're investigating, looking at quantum computers for different types of graph analytics. And there's some machines where there are already results. For instance, D-Wave, we've had access several years ago to D-Wave systems and looked at some graph applications. For instance, there, the workhorse mechanism in D-Wave's adiabatic quantum system was computing a Hamiltonian within a graph, which was the core capability of that quantum machine, which is a direct graph analytic. We're also looking at QCI. I know Steve Reinhardt, currently at QCI, has some new graph APIs for quantum. And other systems, IBM Q, I programmed myself and am very interested in looking at mapping graph analytics to Qiskit on IBM Q's system. So there's a lot of capability that I think quantum will bring to discovering these types of graph features, although there's a lot of work to be done in quantum over the next few years and decades to build larger quantum systems that have more memory error correction and being able to run larger instances.
David, maybe I will ask, can you hear me now?
Yes.
I have a question. You mentioned this epidemic the disease spread model using graph methods. Could you comment on what sort of insights would you get from applying graph methods compared to, for example, agent-based method? Because at ICM we have our own agent-based modeling for Poland.
So that's a great question. And so in disease modeling and pandemic spread, in the past, we've worked with, for instance, the HIV pandemic and spread. And I had a project with Peter Sloot and one of his students, Rick Quacks, looking at there's a common model of disease spread, very similar to agent-based methods for understanding how to track pandemics within populations. Many years ago, I also worked on a problem with Sandia National Labs on immunizing first responders. So how do you decide within a population who should be first in line to get a vaccine in order to protect a population? And we see the fruits of some of that research being used today with the COVID pandemic, where we see different nations and different governments deciding the ordering of immunizations of populations. Also, we've done some work in transportation systems and using graphs to model global transportation, for instance, airlines. And this virus, COVID, SARS-CoV-2, has really showed us how fast a virus from a point in one part of the world very quickly spread throughout the entire world and now has reached every continent. And that requires a deep understanding of the spread of populations and really the airplane networks and other global networks that have combined with models of what happens within a city, what happens within local regions as people live and go to work, etc. So I think the hierarchical graphs on multiple scales give us a lot of insight to understanding how people interact and move around this planet, and understanding that we're in a global world, we're in a global situation, and understanding the impacts of that. How do we influence local decisions to really improve the global outcome? I hope that helped answer the question.
Right. David, I don't see other questions, so maybe I will keep asking my questions. You on one of your slides, you have shown sort of correspondence of graph problems with linear algebra or sparse matrices problems. Are there tools or sort of methods which guide people how to cast one paradigm into other?
So that's a fantastic question, and I've thought a lot about that question. Often it's in the eye of the beholder. For instance, I may think about a graph problem like breadth first search in sort of the graph space, where I have a vertex and I look at its neighbors, versus a friend of mine may view it as a sparse matrix multiplication, and doing one matrix multiplication with the adjacency matrix, still a sparse matrix, and a vector of starting a frontier of the search will give me all the next reachable vertices. So it really depends on how you think about it in your head. I should say that there's a great book on graph algorithms in the language of linear algebra that John Gilbert and Jeremy Kepner co-edited. And I've been a part of a community called GraphBLAS, which is thinking about graph algorithms in the language of linear algebra, that has produced some APIs that are very useful for being able to represent different types of graph analytics through sparse matrix methods. So I'd encourage anyone interested to pick up the book by John Gilbert and Jeremy Kepner as a starting point, or go through graphblas.org and the website for that effort, graphblas.org, that tells you a lot about the view of these problems in linear algebra. And I should mention there's another activity, community effort called LA Graph, and LA stands for linear algebra, and it's creating a very simple, easy to use graph package. So GraphBLAS may require a user with a lot of graph knowledge of how to write graph algorithms to go through and create a solution with a library for solving their graph problem. LA Graph is one step higher, where we're trying to get novice users who know that they have a graph problem but just want a fast technique where they say, compute this on the graph, and really is a much more productive interface to the same GraphBLAS libraries underneath. Tim Davis at Texas A&M University has created a package called SweetSparse that includes one of the early implementations of the GraphBLAS reference software. So I encourage people to take a look at GraphBLAS and also LA Graph, that's emerging and currently in development, if you're interested in thinking about these graphs in terms of linear algebra.
So, David, I still have lots of questions. I'm so fascinated with the topic. You might not be aware, but I've tried several times, unfortunately without success, to bring Cray XMP and Eureka system in Singapore. And right now we are trying to build this graph methods and awareness of those methods at ICM in Warsaw. We are building libraries like Eureka XC on our Cray. We have very nice collaboration with Trovares. You mentioned Trovares, so it's a nascent effort, but would like to extend it. One question: with graphs and also with big data, extremely powerful method is visualization, but graphs are so incredibly fluid objects. And graphing them, trying to picture them on two-dimensional sort of plane is exceedingly difficult. So would you have some recommendations of how to deal, other good methods of visualization, visualizing certain properties and graphs?
So that's a great question. And just to go back earlier, you mentioned Trovares, which I think is a very interesting company. For full disclosure, I served on their technical advisory board, and they're doing some great things with graph software. I'd encourage you to, you and others, to take a look, because I think it's a very interesting company and technology. Now, you mentioned visualizing graphs, and I'm going to a backup slide that I have here called Streaming Seed Set Expansion. So this is just sort of a quad with a thumbnail of results. But what we found is it's very difficult to visualize graphs that have millions or billions, even thousands of entities. It's hard to figure out how to lay these graphs out on a two-dimensional, even three-dimensional visualization plane, and how to walk through these graphs. So what we have worked on is more of a way to get an extraction of a piece or a region of interest from a graph. And this algorithm called seed set expansion is one example of that. So imagine that you're an analyst working on a graph in your domain, and there's a couple of vertices that you kind of want to bring together in the forefront and look at what's around them, what's in their neighborhood. This seed set expansion is doing exactly that. The seeds may be a handful of vertices of interest that you tag and say, well, I want to see what's around these. And what happens is it brings in the region of interest, maybe 1,000 vertices or some cutoff point that you can describe either by number or by some characteristic where the statistic falls off beyond growing the community larger. Being able to abstract and track that community over time as it changes is a very challenging problem. So what I really advocate for is not trying to visualize 1 million or 1 billion vertices that are very hard to lay out, but really to look at pulling out regions of interest at a time and maybe tracking those regions. And this has proved very useful in some real-world applications.
No, thank you. Incidentally, let me make a comment, and also I use this occasion to invite people who are present in the audience to follow the website of ICM, because we also have a very nice relationship with Trovares. Thanks, David, for pointing that out. And regularly we started giving workshops on the Trovares software. And for people who are interested in that, of course, we may make it available for some testing or research.
So some of my collaborators on this graph work, for instance, David Haglin, who was at Pacific Northwest National Lab, is a principal at Trovares. So there's a lot of the ideas that I've mentioned here are with the people and the efforts of Trovares.
Thank you. Do we have any other questions from the audience? Well, I don't see any questions right now. So, David, of course, I can keep asking more and more questions. I can follow through emails. So let me thank you for your excellent talk. This is a very exciting topic. And as I said, we are building expertise in this and the tool set, and we are trying to make those tools accessible to a wider group of people in Poland, although right now there are several sort of highly theoretical works, and I hope that we'll sort of build it into application areas. So thank you very much, David, for your lecture.
Thank you, Mark, and I really look forward to seeing you again, whether it's in Poland, in the United States, or anywhere around the world. I look forward to meeting you soon, and stay healthy and safe. And thank you again for this conversation.
Thank you very much. Thank you very much to all who attended the seminar, and please watch this space, because we will have a seminar on the 18th of March. Quite likely it will be on data reduction techniques for very large data from people from Oak Ridge National Laboratory. And March 18th, we will have a talk about research IT services at University of California, San Diego. Again, very interesting talk. So thank you very much, and thank you, David, again. Goodbye.